Okay, I'm AB, Anand Babu Periasamy. If you dedupe my name, you get AB.
Storage joke.
So I'm one of the co-founders and CEO, and I also deeply involved in the product, tech, architecture, everything. Right. So so getting back to the tech side, these three interesting things that we are working on, and these are all already out. I'll explain. So S3 Express. Amazon actually calls it S3 Express single zone. Actually, it means two things. That it is S3 Express is not S3. It's actually a subset of S3. It's slightly different. Then single zone means that by default, when they give you an object store, it's actually kind of stretched across multi-zone. They couldn't meet the AI demands, the kind of modern applications found on the storage, and they have limitations in terms of number of requests per prefix you can hit. The AI applications in a GPU will eat that up, right? They needed to come up with something that's like as performant as MinIO AIStor. They actually came up with this S3 Express API. Single zone, for us, we supported single zone, multi-zone from the beginning because it's software. How you want to deploy is customer choice. Single zone is not a big deal. S3 Express was something interesting. We actually, very early on, if you looked at MinIO S3 API, it looked like single zone, right? And the S3 Express API, we had some grudges the way Amazon designed S3 API, that some of the things that, while the API is beautifully designed, there were corner cases that they inherited POSIX-like baggage, like listing still has to look like files and folders, subdirectories and sub-subdirectories, and how you navigate the directory namespace, they still gave POSIX-y behavior. That's nice from a legacy application, but for modern AI applications, it comes in the way. And there were a bunch of other details like that. The S3 Express, S3 API was a general purpose API. The AI workload is so critical that if a general purpose API can meet everyone's needs, even AI workloads, if you are talking about the master AI data set, your AI repository, S3 is the right API. But we are talking about pushing the AI workload for all the performance and scale, a general purpose API kind of holds you back. And that's where the S3 Express API comes. And Amazon basically stripped down the API set. And for the API that came in, it's not just a stripped down API. The APIs that are in, like for example, get object, every time you're doing get object, put object, every time you're doing MD5 sum computation, MD5 sum is harder to SIMD accelerate. It comes in the way of performance and CPU. It hits your latency. There are other ways to get the same reliability and durability without relying on MD5 sum. And then the directory, like legacy names, like a directory, a fake directory, things like that, directory tree, walk, all that. Even if you list the objects in a folder, Amazon S3 API would actually sort and give it to you. If you are talking about billions of objects, trillions of objects, sorting is enormous wastage of compute resource for the AI workload. So they got rid of all that. So some of the subset of APIs like get object, put object, even multi-part object and list object, while they look like S3 API, they are actually slightly modified. The list looks like list, but it's not sorted. The get object, put object, there is no MD5 sum requirement. There are other ways you can still do the checksum verification. There are more details, I don't want to bore you, but it's just enough to understand that S3 Express is a subset and a refined set of S3 API. Who is it really useful for? High performance applications. Who are those high performance applications in the modern world? AI workloads, then the database data processing workloads. That is what S3 Express is. We started this way, and then over time, because the community grew, we have like 2 million Docker pulls a day. The community is so large, we couldn't convince the community that this is the right way to do. So over time, we actually relaxed and became full end-to-end. If it works on S3, it should work on MinIO AIStor. That we maintain that compatibility. As soon as AWS S3 Express was introduced, we are like, thank you. Now this is the right set of API. So we actually implemented exactly like Amazon S3 Express API. When you start the MinIO server, you can actually say that you want S3 Express API or you want regular S3 API. By default, it's a regular S3 API. You can actually restart the server and go back to the S3 API. You don't need any data change format. Existing deployments, you can just move over to S3 Express by just restarting it. And that's S3 Express API.
Now, Google introduced something recently similar to S3 Express, only faster. I mean, does it?
No, they don't. Actually, the thing is, right, with Google and Azure, it's not even S3 compatible. Azure completely not, Blob is completely different, incompatible with AWS. Google gave a partial S3 compatibility, but basic things like you upload, like say, a 20 megabyte object, the application would break it up and send multi-part upload. That's broken. Some of the basic things are broken. Otherwise, Google wants you to use GCS API, which is Google Cloud Storage specific API. That's incompatible with S3 API. Even you move from one cloud to another, not just the API, right? Even the bucket policies, right? The security mechanism to access control to everything is different. They are all object store, but they are incompatible with each other. That's where for us, right? You deploy AIStor in Google Cloud, on-prem, edge, your laptop, it's the same experience everywhere, right? And this, I think we touched upon this. I didn't follow the slides, right? So I thought like you were controlling it remotely.
I'm not.
So the benchmarks you can see, right? Here's where you can see the latency, for example, like if you are doing list, if I have a 100 million objects in that folder, I have to sort. And then I start streaming fast, but before the sort completes, I cannot stream anything. So the time to first byte matters, right? The latency shows up in multiple ways. Like even if you see get objects, right? The hashing function, because it has to compute the hash, there's something called ETag. ETag is like in file system world, you call inode. It's a unique identifier for every object. Amazon, for a long time, they made the object tag, the ETag, unique identifier, based on MD5 sum. Now they relaxed it. You don't have to be MD5 sum. It's just some unique identifier. When you strip all these things, the result is better performance, better response time, lower latency. So overall, it actually just, this is the kind of performance AI needs. From AI scale, the performance is actually about scale. Everyone can show performance in a small scale, but when you have these 1,000 nodes, trillions of objects, when you're pounding on it, can you show that kind of performance? Even tiny calls, like every single API call we cut down, it immediately shows a benefit from the application point of view. I'm not going to walk into the performance details in specific, right? Just too much technical details, but we will share the slide deck with you. Now, before I go into GPUDirect, any questions on S3 Express?
Just go back to that one slide.
Sure.
Yeah, that one. Thanks.
Yes. Just in case. There's one more performance deck as well. This one, you got it. So GPUDirect. So for those of you who are not familiar with what GPUDirect is, the modern infrastructure, GPUs are becoming the main processor and CPUs are like co-processor. You load the operating system, you run the Python runtime, all that, but the real workload, the workhorse of the modern application is actually all these matrix multiplication. All of that is actually running on the GPU. The CPU and the CPU memory starts becoming a bottleneck. How fast can you feed the GPU memory? Well, the GPUs are fast. They are only as fast as how the data can reach the GPU memory. And this is where NVIDIA came up with the interface where you can bypass the CPU, you can bypass the host memory, and then directly read and write from storage into the GPU memory. And that's GPUDirect. And NVIDIA started with GPUDirect file and block, because the enterprise was mostly file and block. The cloud was all object. Soon NVIDIA came to realization that the modern AI workloads, born in the cloud, they all need object. And if you look at all from OpenAI to Anthropic to everybody, they are actually built on, from even Databricks, all of them are built on object. So they realized that object, you need GPUDirect. An object, unlike low-level, like a SCSI RDMA, like SRP, there are a bunch of protocols like NVMe or Fabric. Object is HTTP, HTTPS. How do you do RDMA over HTTP? That HTTP Fabric doesn't support RDMA, but HTTP is today the TCP/IP of the modern internet. And all of the, look at the data traffic. It's not fiber channel, right? It's not like regular UDP or anything. It's HTTP carrying bulk of the internet data. And when it comes to the storage, if you see inside every cloud, you will find that object is the traffic, is the data traffic. But it's all at HTTPS layer. How do you mix RDMA here? This is where this is where the GPUDirect object interface comes. So NVIDIA has not announced GA on GPUDirect object yet. We work very closely with them. We have joint pilot customers. The development is complete, the benchmark is complete, and it's showing promise. So why do we need it? Increasingly, networking is becoming the bottleneck. If you put 800 gigabit, still it is the bottleneck. Can I do 800 gigabit today? No, you can't, because PCIe Gen 6 is not yet available on these servers. Gen 5 is there. Maybe you can do dual 400. It's as good as it can get. And still, compared to NVMe drives, compared to the GPU, the network is the bottleneck. But in the network, when we push this kind of data, that data, if you look at the host, these are like the DGX boxes, right? If the data is flowing through the ARM chip, Grace chip, into the CPU memory, and then going into the GPU memory, you want to cut that. You don't want any kind of bottleneck. Increasingly, GPUs are the most important part of your fabric. So the GPUDirect object, the way it works is, from application point of view, is the same S3 API. You do still get object, put object, and all the regular operations. The data that is sitting on your object store that's accessible through regular S3 API is not like you have to migrate that over to different kind of storage. The data is still the same thing, but your GPUDirect enabled application, when they do GPUDirect enabled client SDK, that is when they do get object, they don't actually, the way the get object works is they give the object name, bucket name, just like any other S3 API, any other application, but they will tell, here is my GPU memory pointer. And the data, the get object, all the access credentials, object name, bucket name, goes over HTTP. This is the control channel. It goes to the server, and then server recognizes you are actually doing a GPUDirect call. In fact, the GPUDirect memory is just a HTTP header embedded inside the request call. Otherwise, the request looks like any other get object. When the AIStor server sees this is a GPUDirect get object, it gets the remote RDMA memory pointer. That's the GPU memory, and it's not necessarily one GPU, right? Even single system has multiple GPUs, and you have multiple racks of those servers. The GPUDirect memory pointer is unique. It knows exactly where across the network, which node, which pointer we are talking about, and the server recognizes, okay, now you are asking for this, say, 100 GB, maybe even 10 GB, 10 GB object to be sent to that memory. The server actually then makes a GPUDirect response back. That's a data channel. That's a RDMA channel. It pushes it back. It's also smart enough that if the data is large enough, we can actually break it up into multiple pointers. Then a cluster of servers will push the blocks simultaneously. That way, you're kind of like not bottlenecked by single NIC. You can now push from multiple NICs, and then the GPU machines, as fast as they can take, we can push it in.
Yeah, but I have a question. The network card needs to support that?
So today, NVIDIA says that it has to be Mellanox ConnectX, Mellanox NICs, and Mellanox Spectrum switches. That's what they have validated.
They have RDMA over Ethernet.
Correct. Underneath it is all RDMA over converged Ethernet, right? In theory, it should work for Arista, Foundry Networks, or anybody, right? Edge core switches. But NVIDIA has to validate their software stack. The driver, the driver is today certified only for this. We are ready. It's more like other vendors have to work with NVIDIA to get the blessing.
I have a question here because it's kind of interesting. You disconnect the control plane from data plane, HTTPS. So via HTTPS, you have just a control plane, right? The API calls, blah, 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 just communication, right?
Yeah.
So it don't need much bandwidth.
Correct.
And then you take kind of block data, right? And you stream that block data over the Ethernet with what in RDMA protocol?
Yes.
Right.
Yes.
So it's a pure unencrypted data.
Yes. So good question.
And that means that we have to have one communication layer that it's, let's say, going through the traditional network, and then direct galvanizedly separate channel for RDMA traffic.
Yes. So a bunch of details here. First, the RDMA traffic is underneath is actually built over RDMA over converged Ethernet, right? So that rocky interface. But then if you, what about InfiniBand, right? The Ethernet versus InfiniBand. Enterprises are largely Ethernet based. And if you look at the Mellanox NVIDIA NICs, the same NIC is basically the same fabric. It's just the software layer is different. Otherwise, you get basically the same capability. Converged Ethernet essentially borrowed the InfiniBand ideas into the Ethernet. Now, from a customer point of view, they like Ethernet because they already they took a bet, right? Now, the interface, the software interface to talk to the Rocky layer, if you see what's the library you would use, you will use IBverbs library. In fact, the driver to talk to the RDMA layer is the same code, whether it's InfiniBand or Ethernet. So if you have the RDMA driver, it will actually work over InfiniBand as well. Now, coming to the question, that encryption, right? At this level, nobody's asking these questions. Don't ask, don't tell. Here is a problem, right? Even CXL, same problem, right? Okay, now how about we make it encrypted? Then you don't get the DRAM performance. DRAM is not encrypted. Then otherwise it starts looking like any other Redis cluster or something, right? But the GPUDirect in particular, that the object is encrypted. We can send the encrypted data, but here is the problem. Who is going to decrypt it? The moment someone is intercepting to decrypt it at the client side, the RDMA path is broken, then you need CPU. Can GPU do the decrypt? If NVIDIA enables RDMA decryption, they actually are now working on it. Even compression, for example, they actually have compression function that's GPU accelerated compression, and we already have it. We already have it working in our labs. It looks promising. It is possible to do GPU accelerated decryption as well, but you will take some hit on the performance.
Sure.
Yeah.
Yes. So Mellanox has BlueField chips. It's high smart NICs and stuff. Does it require smart NICs, GPUDirect, or? You
don't need smart NICs for this. As long as even the older, as long as they're Mellanox today, what NVIDIA says is their Mellanox chips, ConnectX-5, ConnectX-6, they are all RDMA capable. So, but typically nowadays the newer deployments are 400 gigabits. So ConnectX-7 is a good bet.
Right.
Yeah, why do you need this? These are basically, if you are GPU applications, right? If you're on the CPU, you can still, the way Mellanox, the NVIDIA guys designed the GPUDirect object is it will work even for CPU traffic. Even if there is a Python application, some application running on the Grace CPU, even they can take RDMA. That GPUDirect object directly makes RDMA call to the host memory. What if it's just a end-to-end Mellanox fabric, but it's just CPU machines? Even that box, the same driver should work. Right? So anywhere you need RDMA class, it's really about CPU bypass on the client side. Eliminating the CPU bottleneck so you can directly talk to the memory is the benefit of it. When you enable GPUDirect object, you will find, if you go to the client machine, you look at the CPU utilization, it will be 1/10 of the normal workload. Otherwise, it's not the throughput itself. Even HTTP can saturate a 400 gigabit network. It's really about reducing the CPU reliance on the compute nodes. Right? So the BlueField. So we have been working with BlueField since BlueField Gen 1. This is pre-NVIDIA acquisition of Mellanox. Right? The BlueField Gen 1, it's basically a smart NIC. It's an ARM chip. Right, like smart NIC, smart drives. Actually, if you look at the drive vendors, all the time came to us and they said, we have a processor sitting on the NIC. It's just sitting free. Can you run on the system, on the controller itself? We said, sure. Right? It's no different from running on a Raspberry Pi, right? It's just an ARM chip. But then our guys just we love performance. It's kind of a OCD problem, right? We went and implemented the neon instructions. Neon is like the CUDA instruction for the CPUs. the equivalent in the Intel world or AMD world. Intel typically AVX512 and AMD is AVX2. Now they actually have AVX512 as well. What's the SIMD instruction in the ARM chip? It's basically neon instruction. So we add the neon instructions, and we Graviton, particularly on AWS, was like so good. It was cheap and it gave the best performance. Now ARM is making its way into the data centers. So this smart NIC made a lot of sense. So all the optimizations we did just worked here. But then we found, hey, there is even a better, wider instruction set, like that's SVE. ARM supports both SVE and Neon. We even did that optimization. All that benefits the smart NIC. BlueField, it's a key requirement. Here's the thing. If the NIC is running, if the smart NIC is the computer, so that means we have to run the software entirely within the smart NIC. AIStor is the only software around in this market that is small enough to fit inside this system, 16 core, right? And just GPU, right? The GPU, the CPU memory, the ARM memory, and the ARM cores, we can run in a low resource environment, but it's also optimized for the SIMD instructions in the smart NIC. These are 400 gigabit smart NIC. We can fit it entirely in. There was a basic problem with this system. Right, that's basically leads to this one. If I bought this smart NIC, and if you told me how do I put this smart NIC in the rack, then if you have to buy a server like AMD or Dell-based server like Supermicro Dell server, then your host processor is more powerful sitting there idle. Then why do you have a proper server and then a smart NIC just to power through a PCIe slot? It didn't make any sense. For sure, the AIStor software ran within the smart NIC, but it didn't make sense to buy a server. So NVIDIA gave the controller to some of these industrial server grade system manufacturers to build servers around it. Finally, this is hitting the market through, like Supermicro is the first one to launch a server. That server has no Intel or AMD motherboard. This is just a smart NIC and bunch of drives and a PCIe switch directly attached to the smart NIC. It's as light as it can get. We actually deployed this at PayPal and few of our customers already. That it looks very promising. What is it? Is simply a JBOF and a smart NIC. Nothing more, nothing less. And that is low power. We all know in the AI world, what's the biggest problem? Power, right? So this is the path to that. And we are the only one who can fit inside this system.